afternoon. Welcome to the tutorial number 8. The last lecture we have this. I hope I am audible. The last lecture we are. Hello. Am I audible?
Yes, sir.
Okay. So the last lecture.
Yes, sir.
Yeah. Okay. So in the last lecture we have discussed about rotational spectra, their selections rules, and if you expect of how the total angular momentum, projection of angular momentum along z-axis, how this is applied on the in spherical harmonics. So now from today we will discuss about the assignment number 7, which is comprised most of vibrational spectroscopy. So let's start and I hope you have gone through the videos and lecture notes. So let's start and you can ask question whenever you have. Okay, let me share now. I hope my screen is visible. Is it visible? Okay. So hello. Hello.
Sir, your screen is visible.
Okay. Let me.
Yes,
start.
sir. Screen is visible.
Okay. Okay. So let's start with the first question. For a diatomic molecule AB under harmonic oscillator approximation, potential energy is given by R square, where statement So if I take a molecule AB in real case, so the potential, if we plot the potential with respect to interatomic distance r, it should look like this. Okay, this is r. Now, so this is an anharmonic case. So in last class, what I have discussed that in the bottom of the potential well, you can consider the anharmonic oscillator as a harmonic oscillator. So in case of bottom of the well, the anharmonic oscillator behaves as harmonic oscillator. This is harmonic oscillator. So this region for a anharmonic oscillator, or you can say the bottom of the well of harmonic oscillator, behaves like a harmonic thing. Now what we can discuss that the potential, okay, is nothing but, if we expand, is v0x dv by dx measured at x equilibrium to x d2v and so on. Now potential is measured with respect to some quantity. For here potential is measured with relative to v0. So we can take this is as a relative, so this can be taken as 0. And also we can discard the higher order term, because this higher order term can be ignored due to a negligible contribution to potential energy. Now at the bottom of the well, so we can treat it as a minima. So dv dx will be 0, as it is a minima. But the second derivative term will not be 0, so which can be written as now this term is a constant. So now this thing is written as written by a constant of k. So we can write at Vx is equal to half of k x square. Now in the question is written at equilibrium. then x will be r or re, whatever interatomic distance. So we can write Vr is equal to half of k r square. Now the k is known as force constant. It actually tells about stiffness of a bond. So if the strength of the AB molecule if the strength of AB molecule is increases, then the force constant will increase. Okay, now if we look at the relationship between force constant and frequency of vibration, so this is nothing but simply written as mu e is 1 by 2 pi k into mu. Now mu is reduced mass. So for AB, reduced mass will be Ma to Mb, Ma plus Mb. Okay, now k into mu. So k is equal to 4 pi square mu to the power square. Okay, so if k increases, means if k increases, that means stiffness of bond increases, then your nu e will increase. Okay, similarly, if mu increases, nu e will decrease. Okay, so now let's look at the options. So for a diatomic molecule AB, k is known as force constant, that is correct, which is an universal constant having for a fixed value. See, this is not an, so first point, k is a force constant for a particular bond, for a molecule, given molecule is okay. Now is universal constant for a molecule is not a correct statement. Suppose you have a carbon monoxide. Okay, it has its own vibrational frequency, but if some different environment, if you keep where the bond elongate, then the your bond strength will decrease, and due to that your force constant will decrease. So therefore force constant and is not an universal thing. It depends on the bond strength of a molecule. So with this statement is incorrect. Next, k can be represented as a second derivative of a potential with respect to r evaluated at equilibrium distance, bond distance. So this is, we see over here, this k is a double derivative. For here you can write as k is d2v by dr2 at r equilibrium. So this is a correct option. Now k is directly proportional to the square of the vibrational frequency. So here we can see this k so if we take this all thing are constant for a given molecule, for a given molecule AB, k will be proportional to the square of the frequency. Okay, so this is also a correct. Now k is nothing but measure of the stiffness of the bond, that what we saw. The k actually tells about the how much strong the bond is. Okay, and is inversely proportional to the reduced mass of a given molecule. No, this is not correct. As we can see, the k is proportional to the mu. So with this, actually this statement come to incorrect, because as k is proportional to reduced mass. Okay, so for question number A, for question number 1, B and C are the correct option. With this, let's look at the second question. Eigenfunction for a harmonic oscillator AB is given by x is nv exponential x. The correct statement respect to the function of a free particle in a box. Represents a modulated Gaussian function. given expression So if we look at the picture of a harmonic oscillator, the Hamiltonian is nothing but plus Vx, where half of kx square. So a particle will call a term that or call as a free particle when that molecule feels or particle feels no interaction, because interaction is denoted in quantum as a and anything is as a function function of potential. If there is no potential, then there a molecule will be called as a free particle. But in case of harmonic oscillator, there is always a half kx square term which contributes to the potential of the Hamiltonian. Therefore, a harmonic oscillator, a particle behaving as harmonic oscillator cannot be a free particle. Okay, so the first option is incorrect. Sorry. So this is not a free particle in a box problem. Okay, now chi v e x represent as a modulated wave Gaussian wave function. Now if you solve this function, then there is different ways to solve this Hamiltonian. So the standard way that demonstrated in the lecture is using Hermite polynomial, which gives you the version of your wave function is something like a normalization constant with the exponential term, and there is a Hermite polynomial. Now if you carefully look it, so this value is just a modulation factor. So depending on the alpha, v value, where v means vibrational quantum number, you can have the different values of Hermite polynomial. But the main factor of the wave function is the exponential alpha x square by 2. So what it's actually saying, it's in the nature of the nature of the plot or wave function will be a Gaussian in nature. Where your Hermite polynomial will act as a modulator. It will talks about the shape, or and this term is nothing but a normalization constant. So the option number B, what is says a modulated Gaussian wave function. So this is a correct one. Which so this factor is this is a modulation. This is a modulator factor, and this is a Gaussian. Now and see the given wave function HB is now known as Hermite polynomial, which acts as a modulated which is I show it here, which is correct. Now in the given expression alpha, so this alpha, so the expression of alpha is mu into omega by h cut, where mu is the reduced mass, omega is the frequency of vibration, and h cut is Planck constant divided by 2 pi. Okay, so now what this alpha means is a owing factor of the wave function. Okay, now you can see this mu term, sorry, this omega term. This omega is talk about the frequency of so alpha is no longer remains constant if the vibration frequency changes. So if omega changes, of omega is there na, so is angular, right, it is angular vibration which is nothing but 2 pi mu. You can put a e here over here, where nu is the only vibration. As the omega e changes, the owing factor alpha will no longer constant. So therefore this option is not correct. Okay, so this is the, so B and C is the correct option for the question number 2. Now let's look at the question number 3. Transition integral EMI or a rational transition of for the transition to be happen from the first class we not first class, from the first 2-3 class we saw that it depends on the factor now transition moment integral. So if it's 0, there will be no transition. So for a fruitful transition the value should not be 0. So where you can see the expression of transition moment integral after few deduction is something like this. Now this is something called transition dipole. Now the transition dipole is not actual permanent dipole. Okay, it means something else. Yes. Hello.
What is the maximum
Huh?
value of transition moment integral?
No.
What is the
See,
maximum value possible for transition moment integral?
See, depend. See, if it's 0, it is not possible. Okay, this maximum value should be anything. It cannot be said like that. Is a finite number, so it depends on if it non-zero, it is allowed, but the maximum value is cannot be said like that. Okay, it is depends on the what the transition dipole moment, the bond distance, and the quantum number from where it's getting from quantum number from where it's originating and where it's getting transformed. Okay, so the maximum value cannot be said. Okay, but but the thing is that it should not be 0, otherwise it will be forbidden. Okay, so the transition dipole is not the permanent dipole of a molecule. It has something other. Okay, so this first option is eventually incorrect, and second option is nothing but corollary of the first question. So mu can be expanded as a Taylor series. So now this mu 0 is the permanent dipole moment. Okay, and the rest of the term is the derivatives of mu, which are with respect to the equilibrium distance of a molecule. Okay, so this thing is correct. Now we will use with the course of the today's tutorial, we will see the how it is being used. In previous lecture we saw it how we use this thing in rotational term. Here we will use it in a vibrational term. Okay, so now the third option is saying in the given expression m must not be equal to n for a transition to happening, which is correct. Otherwise, see, if it's ending in the same state, doing this exercise is not valid. So it's always m not equal to m, and we will see how it's not equal to n, how much is the values, and what are the which are the selected values for m and relationship between m and n in the next question. And then fourth one, in the Taylor series expansion, the what is the question is written? I am reading the wrong thing. Now the higher order derivative can never be neglected. So in case of vibration, we will neglect the second order derivative of mu because it's contribute negligibly. Okay, so it can be neglected. Okay, next let's do the mathematics, and so we'll do it like little bit amount, not the whole thing. So as I mentioned, the mu is written as mu 0 and mu e, sorry, mu is written as mu 0 only x. Now what is our TMI? Now if we write now, this thing is a constant term, so it will come out, and we can take okay. So now we know for a so that we know. Now this form a complete basis. Now if it completes basis, so therefore this term is mutually orthogonal. Psi m and psi n are mutually orthogonal. If m is equal to n, then this delta mn will be 1, otherwise delta mn will be 0. So as we said here in the previous question, n and m should be different, therefore this term will be 0 and only this term will tell us the selection rule. Okay, now what I mentioned here, so you can take mu dash xc term also out. Okay, now what is the expression of n is h, sorry, is nothing but n h n exponential alpha x square by 2 by similarly same. Now if we write like this, so this will be nothing but, sorry, exponential alpha x square hm x hm. Maybe we can take it okay. Now we know for 2x into alpha hn it will be hn plus 1 and 2n hn minus 1. So x hn can be written as so hm alpha by 2 hn plus 1 into n alpha n minus 1 exponential. Now we can write it separately. Now look at that these two integral. These two integral is only survive when m equal to n plus 1 and m equal to n minus 1. Therefore, for a so for transition, the selection rule is like this. Okay. So all the selection rule or delta m or delta n, whatever you can say, are derived based on this kind of condition, where it appears that the integral is only surviving when this the integral the transition is only surviving when that integral is survived. Okay. So this is the selection rule for vibrational transition. Now you can with this idea we can quickly solve the question number 4. Number 4. Now you can the option can be chosen from the derivation what we have done previously. So what he is saying that the TMI can be divided in two parts. So this is nothing but similar to the expression what we write over here, this thing. So this is the permanent dipole moment, and this is only survive when m equal to n, and this expression will be mu 0 into so when m equal to n, the delta mn value will be 1, and in that case it will survive. Okay, so option number 1 you can say correct. Now for option number B, mu prime xe represents all the higher order derivatives of the dipole moment with respect to bond distance evaluated equilibrium bond distance. So here you can see that for the here you can see that the transition dipole is written as a Taylor series expansion of permanent dipole moment with additional to higher order terms. The higher order terms is neglected due to their negligible contribution to the transition dipole. Therefore, it's only constitute with the permanent dipole moment and the first derivative of the permanent dipole, first derivative of the transition dipole moment measured at equilibrium distance. Now you can see that this thing is the first derivative is represented by mu comma xc. So it's only denote the first derivative, not higher order term. So with this thing is incorrect. The mu prime xc is only denote the first order term of transition dipole. Now option number C is saying, according to given expression, selection rules for vibrational transition is given by mu xc not equal to 0, which is correct. Otherwise, if the mu x e, this term, is gone to 0, nothing will survive. So this must not be equal to 0. Okay, but what it says, m equal to m. So if m equal to m, then the term will be then you will get so no transition. That doesn't mean the molecule is the same area. So that is not we need. Okay, so this is also incorrect. Sorry, because we need to excite molecule from one state to another state. So and the last thing what is written over here, according to the expression, the selection rules for a transition is given by mu x not equal to 0, that is correct, and m is equal to n plus 1 or m equal to n minus 1, should be n minus 1. So this is a correct option what we see in the derivation. So for selection rule, mu xc must not be 0 and delta n plus minus 1 or delta m plus minus 1, whatever. You can write delta n only. Okay, now let's switch the gear from vibrational selection rule to little bit of electronic transition. Okay, so question number 5. The transition moment integral electronic transition from the ground state to state is given by okay. So this is a transition moment integral for a electronic excitation. Okay, so now if I look at the transition moment integral, get a full form. So the full wave function can be written as a is dependent on nuclear wave function and as well as electronic part. So electronic part is parametrically dependent on the nuclear coordinate. So therefore, if we take account the transition from ground state to excited electronic state, then we have to incorporate both the electronic transition dipole moment as well as nuclear part. So therefore, the total transition dipole moment can be written as now you can according to Born Oppenheimer approximation, the motion of the nuclear part is very slow than the electronic thing. Okay, so if you see like this is a, for a molecule this is a ground state and these are the vibrational state, then and now if you excite it to some, so this is a G state and this is a E state. Now if you want to excite it, it will vertically excited to the this. So while excitation, your nuclear part is doesn't change. What change? The electronic part. Okay, so now it's become ground state to ground state to excited electronic structure. Okay, so now let me complete this thing. Okay, so this now, so we can neglect this part. Okay, and this thing is known as Condon approximation. So now the TMI is becomes only electronic part. Now if this transition moment integral survives, then your transition will take place, otherwise it will be zero. Okay, now in the expression what is asking that for question first option mu EL and mu GL are electronic wave function, okay, and they do not depends on the nuclear coordinate. So whatever we can see that electronic wave function is always dependent on the where is the position of nucleus. Otherwise, in the potential energy surface, it cannot be the position of a particle in the potential energy surface cannot be specified. Therefore, electronic wave function is always parametrically dependent on the nuclear coordinate. Okay, so the first option is thereby is incorrect, where the second option is correct. Now operator mu EL act as a both electronic and nuclear wave function. Okay, so you can see that that mu electronic is only act on electronic part. Okay, so as we mentioned, if we go derive little bit, so it's actually if we write it both in nuclear and electronic part. Actually it's not d tau dash you can also add, because this is double derivative, one is electronic part, one is nuclear part. So you can write just as I mentioned, the nuclear part doesn't change while transition, so mu el is only acting on the electronic part, okay, not the nuclear part, because this term is remain constant while the electronics exciting, okay. Now operator mu el, so this is a correct one. Okay, with this question number 5 is done. It's a little bit glimpse of UV electronic excitation, and now we will look few more thing about rotational spectra. Now let's look with different types of rotors. Okay. So question number 6 is asking non-linear polyatomic molecules can classified as spherical, symmetric and asymmetric rotors. So molecule can be divided in three major parts, okay, depending on their rotations. So For a polyatomic molecule, non-linear polyatomic molecule, it is spherical. Second is symmetric rotor or symmetric top rotor, and third is asymmetric rotor. So if a molecule is as a molecule is a non-linear molecule, you can think as a three-dimensional molecule. So there in three different axes they will have three different axes and different moment of inertia. So if the moment of inertia in three different axes are same, then it will be that kind of molecule is classified as spherical molecule. The classic example is methane. So if a molecule this symmetry point group is tetrahedral, no? So the minimum requirement for a molecule to be a spherical rotor is at least two non-coinciding axes of symmetry with, so here you can have C3 and C4 symmetry, okay, and which are non-coinciding. Now spherical rotor, then what will happen? Two axes are same and third axis is not equal. So it can be written as, so IA equal to IB can be like this. Either greater than one axis or less than, either two the moment of inertia around two axis is greater than the third one, or otherwise the moment of inertia is one axis is greater than the rest of the two. Okay, so now depending on these two, there is the molecule is the symmetric rotor molecule is classified in two different versions. So this kind of molecule is classified as oblate, and this kind of molecule is classified as prolate. So oblate molecules you can think as a disc like or cake type. The prolate molecule is actually like cylindrical in shape. Okay, so these are the two different class where one CN axis is there with n greater than equal to 3. Okay, now asymmetric rotor. So asymmetric rotor is nothing but both all the three not equal to is not equal to each other, and for here you can think that this value is also not equal to 0, and this value also not equal to 0, and this is also not equal to 0. Okay, otherwise the symmetric top molecule will be a linear molecule because there is two. Okay, now for asymmetric rotor molecule, the criteria is molecule which do not have C3 or Cn where n is greater greater than or equal to 3. Therefore, water is C2B symmetric now. So it will be classified as asymmetric molecule. So these are the classes of polyatomic molecules with their example. Okay. Now the question what is asking here, for a spherical rotor contain more than one non-coinciding symmetry axis Cn where n is greater than or equal to 1, which is the criteria of spherical rotor, which is correct. Now methane is a symmetric molecule rotor. So this is as I mentioned, methane is not a symmetric rotor, is a spherical rotor. However, the condition is written in the question is correct, but methane the statement showing that the methane is a symmetric rotor is a incorrect statement. Now benzene is a polate rotor while ammonia is a oblate. So as I mentioned here, the oblate molecule is a disc like shape. As you can know that benzene is fat molecule. You can compare as a disc type of shape having six as a principal axis. So benzene is oblate, where NH3 will be prolate. So both of them are symmetric crop molecule because both of them possess Cn axis greater than 1 greater than or equal to 3, like NH3 is C3b symmetric, where benzene is D6H symmetric. Okay. Now so this is a incorrect one. Now water molecule is a asymmetric rotor because water is a C2B molecule, and C2B molecule is asymmetric rotor because the moment of inertia along three different axes are not equal. So this is a correct one. Now moving to the seventh question. spherical rotor, we know all the three rotation are equal. Okay, Ia equal to Ib. This is correct. Now the spherical rotor molecule have no have no dipole moment, have net dipole moment, and hence pure rotational spectra can be observed. But you can see it is not true, because if you take the example of CCl4 or CH4, the net dipole moment is 0. If the net dipole moment is 0, then there will be no pure rotational spectra. So for a spherical rotor, you cannot see any pure rotational spectra. So this is a incorrect option. Now the energy of rotational state corresponding to quantum level J is given by Bj, J plus 1, where B is the rotational constant. So this is a correct one. Now the each rotational level has symmetry 2J plus 1. Okay, but the thing is that for each J has symmetry J plus 1. Now for each J there is a projection along for each J there is a it's a rotational quantum number, and each rotational quantum number is a projection and in the space, which is known as mj. So that will also contribute, which is has a number of 2j plus 1 for a particular j, that this rotational in the space will have the degeneracy of 2j plus 1. So if we multiply, degeneracy can be multiplied. Okay, so this is nothing but 2j plus 1 square. Okay, so this is not 2j plus 1 fold degenerated, is 2j plus 1 square degenerated. So for details of this information, you can look at Atkins. The book is Atkins Physical Chemistry. Okay. So for spherical rotor, each rotational state has 2j plus 1 square fold degenerated. So this is an incorrect option. Okay. Now moving to question number 8. the symmetric rotors, we know the three among the three moment of inertia, two are equal and another one is not equal to both of other two, and all the moment of inertia are non-zero. So with this, the first option is correct, and whatever the relationship between the moment of inertia, we have seen it can be classified into two different part. One is polled and another is oblique. Okay, so the now if you derive the expression of symmetric top molecule, it would look like this. So how to derive it? It's written in the way of deriving is very straightforward and written in Atkins. You can look at. Okay, so now we know the J term. J term is nothing but rotational quantum number. Now what the K terms is? K term is also a quantum number. Okay, now you can think that for a spherical molecule, all the axes are same, and therefore the J value is enough to determine whole the angular part. But in case of symmetric molecule, two of the among the three, two of the rotational two of the moment of inertia is equal, but third one is not. So therefore we need another quantum number to describe the rotational motion. Therefore the K is incorporated is also a quantum number which denotes the projection along the J axis. Okay, so now while deriving the selection rule, it is found that this for selection rule for symmetric rotor is delta J plus minus 1, but K value is 0. Okay, delta K is 0. So this option is incorrect. Now K has no contribution to pure rotational spectra. Anyway, the thing is that it is already told that it's a rotor approximation. Okay. However, the K term is there in this equation. Now, the K value for here is 0 to plus minus J. So for K will contribute to pure rotational spectra. Okay, so because for our transition from because each K has effect on E levels. Okay, so K has contribution to line spacing. Okay, now for D, so K has contribution. Now if we talk about E, you can see that from the selection rule, the delta K is 0. Then only the first term will survive for according to selection rule. Therefore the line spacing will be 2b. So option number D is correct. So this is a correct one. Okay, now moving to the last question of the session. from the selection rule we know the for select for uh, transition, the delta j value is plus minus 1 and k should be 0. So this is a correct option and this is a incorrect one. Now it is written over the centrifugal distortion is working now. So now the total expression should be changed. Now we have to, in centrifugal distortion, the expression for symmetric rotor molecule become jk bj j plus 1 a minus b k square. This is up to now dj j square j plus 1. Now jk j into j plus 1 into k square dk k to the power 4. Now for transition, now it will become 2j j plus 1 into b minus 2j j plus 1 square. Okay. The quick math you can do by yourself. So now the line spacing is no longer 2b. It has so many terms. This has 2 dj term, djk terms and k square term into it. So this is no longer correct under centrifugal distortion. Now k will now have an effect on the line spacing in the rotational spectrum. So which is the correct one, because you can see that third term has k. So now in centrifugal distortion, k has effect on the line spacing in rotational spectrum. So these are the 9 questions which are asked in the tutorial in the assignment 7. So we are done with the question assignment number 7, and now you can ask anything about the tutorial. Otherwise we will stop it here. Yes.
Is this the last tutorial?
No, I have. I think I haven't one tutorial class extra on 18th. I don't think it's floated out, but I have applied for another tutorial, extra tutorial on 18th, where we will discuss on assignment 8. Anyway, the assignment, the tutorial is. The assignment 8 is based on some electronic structure calculation, some electronic structure thing. Anyway, in tomorrow's class, maybe Shavi will take both of them together, and if I got the extra class slot, we will go to the we will discuss on assignment number 8. Okay. So
Okay, sir.
officially this is the end lecture, but as we are not we are not discussed the essay number 8. So on the extra session we can discuss about it.
Okay, sir. Thank you.
Hmm. So is there anything else, or I can stop it here?
No, sir.
Okay, thank you for joining.